One more thing to talk about with aromatic hydrocarbons is oxidation and reduction. We've talked about reduction before with hydrogenation when we discussed alkenes, but aromatic rings are more stable and do not react under normal conditions of hydrogenation. So when we look at this problem here, we have an aromatic ring. We also have an alkene. And so what would we expect for a product? Well, the aromatic ring should remain intact, but the alkene is reduced to an alkane. If you want to reduce the aromatic ring by hydrogenation, you need more extreme conditions. So usually higher pressure and also temperature. Here in this case with orthoxylene, it seems to work at room temperature, but a very high pressure, 130 atmospheres. A lot of times you see also an elevated temperature to go with the pressure. Oxidation is also not as easy with a benzene ring, but the ring itself doesn't oxidize, but we can look at the alkyl side chain. So if you had like toluene, for instance, that methyl group on the ring can be oxidized. And we use KMNO4 or either dichromate or chromate, usually in the presence of acid. The carbon bonded to the ring must have a hydrogen on it, and the remaining carbons become carbon dioxide. So let's say we want to oxidize butylbenzene. So we have our butylbenzene, and we might use KMNO4 with acid conditions, and the ring will remain intact. But the carbon that's attached to the ring becomes a carboxylic acid. And what happens to the other remaining carbons? They become carbon dioxide, and we have 3 of those. What about tertiary butylbenzene? Well, here's our tertiary butyl group, and say we go to oxidize that, we will get no reaction. And why is that? Because the carbon bonded to the ring must have a hydrogen on it. There is no hydrogen on that carbon, so we can't oxidize that carbon without breaking carbon-carbon bonds. So let's take a look at some oxidation reactions we've looked at so far this semester. Here's our benzene. If we oxidize this chain, the benzene ring becomes, the benzene ring remains, but we oxidize the first carbon to a carboxylic acid. And we have 1, 2, 3, 4 remaining carbons on that chain to become carbon dioxide. Now you might recall MCPBA, that's how we create an epoxide. In this example, and then when you treat it with water, it opens up the ring. Like so. We also talked about oxidizing alkenes with KMNO4, and if you do it in basic conditions, what happens? you get an addition reaction, hydroxylation, and it was syn addition, if you recall. So these were complementary methods if we wanted to get either cis or trans hydroxylation. We use one of these methods. And then finally, KMNO4 with acid will cleave alkenes, as you recall. You cleave this right here. Remember, there's an H here. So we end up with carbonyl. Each carbon of the double bond becomes a carbonyl. And as I said in class, this usually, this aldehyde usually further oxidizes to a carboxylic acid. So let me clean this up. We have 1, 2, 3, 4, 5, 6, 6 carbons. 3, 4, 5, 6. And that will become a carboxylic acid. And then another example of that, here we have a diene, and we cleave these two double bonds. Notice this one has 2 hydrogens on it, and as you recall, that will become carbon dioxide. So we get CO2. This part here will become acetone. And then we have 1, 2, 3, 4, 5, 6, 6 carbon chain. And on carbon 2, counting from this end, not necessarily for nomenclature, but just to keep track of things, we have a carbonyl, and that's a ketone. 3, 4, and then on 5, there's another carbonyl, and that's a ketone. So those are some different oxidations that we've looked at this semester so far.